All right, we are going to try a Khan Academy-esque kind of a thing here because I couldn't find a good video on Khan Academy to cover inductance. So I'm going to try to do it myself, and we'll see how spectacular this failure turns out to be. We are going to talk about inductance, and you know a thing or two about inductance already, so let's go over the things that we do know. If I have a coil of some number of turns, doesn't matter how many, I'll draw my nice coils right here. Okay. And I've got it connected to some power source, say a little voltage source like this. And I have it connected so that there's a current going through this coil this way. What I can figure out from the right-hand rule is that I induce a magnetic field that points this way. Not too bad, right? Okay, well, let's make life a little bit more complicated. And let's talk about maybe putting another coil in the same area, which we've done before. Put it right here. I'm going to give it some number of turns that's maybe different from the first coil. I'm just going to close the loop right there. What happens with this second coil over here? Well, we know right away that in this second coil there is a magnetic flux. I'm going to call this phi B2 because this is actually coil 2 and this is coil 1 right over here. And that magnetic flux is equal to the B field generated by coil number 1 times the area of coil number 2. So far, so good, right? Okay, well, let's make it even a little bit more complicated. And let's say that this magnetic field in coil 1 is time dependent because this current down here is also time dependent. It changes with time, so the B field generated by coil 1 also changes with time, meaning the flux over here in coil 2 changes with time. Well, what do we know about a changing magnetic flux in a loop of wire? We know that that gives rise to an EMF in coil 2 is equal to the negative of number of turns in coil 2 times the time rate of change of the magnetic flux in coil 2. Okay, not too bad. We've seen this stuff before. Now, some things that we know. We know, for example, that the magnetic field generated, can't stop pressing this stupid little button. The magnetic field generated by coil 1 is proportional to the current in coil 1. And we also know that the magnetic flux in coil 2 is proportional to the magnetic field generated by coil 1. Right? So we can see phi B2 is proportional to B1, which is what we're saying right here. And B1 here is proportional to I1, which is this guy over here. Okay? So if we know that B1 is proportional to I1 and phi B2 is proportional to B1, we can write the relationship between these things this way. N2 phi B2, right, is equal to something we'll call M times I1. And basically what we're saying here is that the flux, the magnetic flux in coil 2 is proportional to the current in coil 1. And we're saying that because the magnetic flux in coil 2 is proportional to the magnetic field generated by coil 1. And we know that the magnetic field generated by coil 1 is proportional to the current in coil 1. Now, this proportionality constant right here, this M that we've invented for ourselves, what the hell is that? Try again. M is what we call the mutual inductance. Okay? All right, so far so good. All right, well, let's play around a little bit with the mutual inductance. We'll define it and figure out how to determine what it is and use it in terms of the other things that are interesting to know about these coils. First of all, I'm going to write that equation down again, just so I have it in mind. Wow, this is terrible. So N2 phi B2 equals this M mutual inductance times I1, right? Now we can do a couple of different things with this equation. First, what we're going to do is we'll take the time derivative of both sides. Why? We'll see in a second. And what we do when we take the time derivative of the left-hand side right here, the n number of turns in coil 2 is constant, so we can pull that out of our time derivative. And what we're left with is d by b2. It's really awkward to write like this. By dt equals the time derivative of the right-hand side. And since m, this mutual inductance, is constant, we're going to pull that out. And say this is equal to di1 through dt. There we go. Well, this left-hand side we just recognize as the EMF in coil 2, right? That's the negative of the EMF in coil 2. Right, we replace this with E2, and we can say that E2, or the EMF generated in coil 2, is just equal to the negative of the mutual inductance times di1 by dt. Awesome. So we can figure out what the EMF in coil 2 is if we know this proportionality constant, the mutual inductance, and we know what the time rate of change of the current is in coil 1. And because of the symmetry in the universe, we can swap all our subscripts. And the same is true in reverse. The EMF in coil 1, if we change the current in coil 2, is simply equal to the negative of the mutual inductance times di2 by dt. Okay? Great. Might be able to use those to solve some problems later, hint, hint. And I'm going to move on to the second thing that we can do with this equation now, and that is solve for the mutual inductance. We can use this equation to figure out what the mutual inductance is and figure out a number for it. It's got a number. And I'm going to just solve this for m right here. You can divide both sides by I1. This is going to be N2 phi B2 over I1. So if I know what the number of turns in coil 2 is, I know what the current in coil 2 is, and I know what the magnetic flux in coil 2 is, I can calculate this mutual inductance. And because of the symmetry of the universe, again, I can change all of my subscripts. The exact same thing works in reverse. Over I2. Okay, so if I know what the number of turns in coil 1 is, and the current in coil 2 and the magnetic flux in coil 1, I can also calculate the magnetic inductance. And the mutual inductance. And this is going to be the same no matter which way I do these calculations. So there you go. That is mutual inductance in a nutshell. And one more thing before we leave, the units of inductance, that's a horrible N, equal henries. Okay, so when you see something in henries or with a unit H on the end, you know you're talking about inductance. And that's it. Hope you guys have a great day. We'll see you tomorrow.